Okay, so first thing is looking forward. Is I'm going to get it out to you on Blackboard either tomorrow or Friday. It's turning out to take a lot more time to set up these classes than it was for in class, so I'll see when I have time to do it. And due in a week and a half, not next Monday, but the following Monday. This will be like, I think I put this on the announcement. You can work in groups of up to 3, like the computer lab. And one day next week, which I'll decide by tomorrow, we'll just gather maybe Zoom. I don't know if Zoom is better than this. I'll have to look. Where you'll just come in and start working in groups. So I can start putting together groups and so on. And like the computer lab, this is completely open, so you can talk to each other. You can work in big groups bigger than 3 if you can find each other, but you're going to hand in for a group of 3. Sorry about the writing. In some ways, what happens after this will depend on how this works. So there will be a test 2. In about 3 weeks. And then besides that, we'll see how the take-home goes. If the take-home works out okay, there will be another take-home, which will give us what we had on the syllabus, 4 quiz grades and 2 test grades. But that will depend on how well the take-home goes, see if there are any problems with it or not. The test, I'm not sure exactly how that's going to go. Sometime next week, I'll start talking about what day we'll try it, and I'll have to get what time zones everyone is in so that I can send it out at different times. But we'll deal with that later. So that's sort of what's coming up. I should say before I actually start this class is like the last class and like the ones this morning, the audio will sometimes go in and out. I'll have to play with it. I'm not sure exactly why. I'm not sure if it's a connection or whatever, but if you can't hear me, send a chat message and I'll stop, try to fix it. I have a microphone. Sometimes if I plug the microphone, it works better for a little while, and then it stops working, and I take the microphone out, and so on. In terms of the actual groups, probably easier if you form them yourselves. So you'll get that either tomorrow or Friday, depending on when I have time. So that's what's coming up. And as I said, we are roughly following the notes that are now on Blackboard under, I think, old notes or something like that. So any questions on what's coming up quickly? So in some ways, instead of raising hands, it's probably easier to just write in question on chat. So ask, could form a Blackboard discussion. I should be able to. As I said, what I might try, which is what I did for office hour stay, was with Zoom, which is a bit nicer. I can more easily assign people into groups and so on. So I'll play with it for the next couple days and we'll see what goes on. And like the lab, you do not have to work in groups. So you can work on it yourself. Also, I should remind you, like the last one, last time, there's a bit of lag with the chat. So you'll be hearing me stop for a minute to give a chance to questions to come in. So if I'm just saying nothing, it's because I'm waiting to see if something comes up. So any other questions on this setup? The other thing is, remember, I can't erase part of it, so I will erase and then we'll start the new thing. Okay, so erase. So what we're going to start with is we want to get the density function for MM1. Because what we want to be able to do is, for example, find the median time I am going to be in the store or whatever I want to call the server. So how long I am in the store will depend on how many people are there. So what we're going to have to do is break it up into conditional probabilities. So first case, I get there, there's no one there. So in that case, the time I wait there will have a density function of an exponential with a parameter of mu. And therefore, I can write it this way. Sorry about that. Let me rewrite that. Somehow it's catching my finger and doing weird things. So we get that is the initial density function. When I get there, there's no one there. If I get there and there's one person there, then it will be the sum of two. And we looked at this way back when, and I think we actually solved for it, but right now I'm just going to give it to you. Right, so what's behind the scratch is also written on the next line. So this part, let me just erase because this part I repeated in the next line. So if there's one person, it'll be the sum of two. So it's going to be the sum of two things. So the density function n is equal to 1 will be the sum of two. And it will turn out that that is going to be what's called a, so let me do an aside here. Is that the sum of m plus 1 independent exponential distributions is what's called an M-Erlang distribution. And I'll go to the next one to write down what that is. As I said, we sort of did that. We looked at how you get the sum of two exponentials, which is we would look at a double integral, assume they're independent. You can get the joint density function by multiplying, take the antiderivative, and so on. So we did it near the beginning, but we're not going to continue. So as I said, I'm just going to give it to you. So any questions before I erase? Okay. So I get that. And you can see that a zero Erlang is just the exponential, because if I put in n equals 0, I get the mu t to the 0, which is at 1, and 0 factorial, which is 1. So it's kind of a generalization of the exponential. So let's go back to the thing. So if there's one person, mu t, yeah, so mu t to the m. So this is m. Okay, so if I put in 1, I get mu t to the 1 over 1 factorial and so on. So if I get there and there are two people, and so on. So there's a conditional density function. So to get the general density function, I need to put it together. So we know from before fixing my writing, so sometimes it makes it weird. That's probability n is equal to m, 1 minus rho times rho to the m. And remember, rho is lambda by mu. Therefore, the general density function will be equal to, and let me put it first in notation, that. And now I'll put those two together and to put in our formula for probability, our formula for the conditional density function. So let me give you a minute to check to see if you have any questions. Erase. This is the mu e to the negative mu t is the density function when m is 0. When n is 0, 1 minus rho is the probability that n is equal to 0. density function when n is 1 and probability that n is 1. Look at that. And so this might look a little bit more like something you know. Again, it's fixing some of my things. So that should be after the ratio, that's a mu in front of the e to the negative mu t. And then 1 minus rho times rho to the m. And we can pull out some of this and combine other parts. None of those have an m in it, so I can pull that all out. And I get that. And this we come up to a few times. Does anyone remember what the Maclaurin series that is from? Yeah, so that is e to the something. So if you have x to the m over m factorial, it's e to the x. So therefore, this part is e to the mu t times rho. And since mu times rho, since rho is lambda over mu, this is equal to e to the lambda t. Putting it together, also notice that I can do the same thing here. Mu, if I distribute, I get mu minus rho times mu. Rho times mu is again lambda. And I get this. And putting it together, it forms this. So it actually ends up being a fairly simple thing, as with most stuff from MM1. So this is the density function for the time we have to wait that we're going to be in the system altogether when I get there. And I don't need to know how many people are because that's the general probability. Why that? Why that one equals to e to the mu t? Are you talking about this part? Okay, so here, let me put over here, sorry about that, is I know that e to the x is this Maclaurin series. So you don't need to know that, but it's come up for us a few times. So that is Maclaurin series for e to the x. And if you compare this to over here, you'll see that what's inside the parentheses is going to be called our x. Therefore, we'll plug what's in the parentheses into the actual. Okay. So any questions on this before we actually use it? So here is how t of t. So any questions before I do an example? And you'll see that's pretty easy, like most of MM1. I'm kind of doing weird things with my writing. If we have an MM1 with lambda equals 3 and mu equals 5, that's find the median time I'm in this system in total. So the time I'm in the system is t. Therefore, the formula for the density is the one I just got, which is mu minus lambda e to the negative mu minus lambda t. And we just get this nice, easy density function. And once we have it, then I can use it to get the probabilities. So for example, the median is the number m so that on whichever side you want to do, is the number m so that the probability m less than or equal to it is equal to 0.5, or equivalently, the number m so the probability m more than or equal to m is equal to 0.5. And I know the probability less than or equal to m is the integral from 0 to m of the density function, the one we just got. And kind of going backwards, when you plug in m, you get negative e to the negative 2m. When you plug in 0, you get 1. So I'll flip them to make it this. And so we have a fairly simple exponential equation that we can solve for m. I think we've done one similar to it. So subtract the 0.5 from both sides. And then, of course, we take the natural log of both sides. And as always, you're going to double check my numbers, but I get something like that. So any questions on this? As I said, like much of MM1, it's fairly straightforward. Getting the density function is kind of a pain, but once we have the formula, it's pretty easy, just the mu minus lambda e to negative mu minus lambda t. Okay. So any questions on this before I erase? All right, so now I'm going to do a finite example, which, and I'll write it down. This is problem 8 in the homework in the second part of the section. The reason I'm saying it that way instead of the page number is I redid it, and the page number will depend on which version you have. So I'll just write down the question. So we have the finite case MM12, where 3 people per minute are arriving, and it takes 15 seconds to serve a customer. And we might, as a review, do all the questions and then add in the time thing. So we'll first find the steady state probabilities. And for this one, we could get a formula, as I said last class, or the class before, I forget, but it's easier just to draw it, and especially because this is really short. Either there's 0, 1, or 2 people in the case. The arrival rate is 3, as long as it's not full. So in some ways there is a 0 here, but we don't really care. What is mu? So I just directly give you lambda is equal to 3. You have to do a little calculation. Mu is equal to 4. Because remember, we have to do everything into the same time interval. So in a minute, we get 3 people. In a minute, we'll serve 4 people. And go back to the simple one, because since there's only one server, the departure rate is always 4. For this, remember, when we're drawing it, solving for the steady state, we can just read off from before. So P1 is equal to, and if I look at this, I get it's 3/4 P0. And P2 is equal to, again, the 3/4 P1, which is 9/16 P0. Well, it's the mu is how many customers are served in a given time period. And we just have to make it the same as what we're using for lambda. So lambda, we're doing it per minute. So we have to do it per minute also for the number served. And then we know that if we add up the 3 probabilities, it adds up to 1, P0 there. That's supposed to be a 37/16 P0. So when I divide through, I get P0 is equal to 16/37. Well, so we sum P0, P1, and P2 because the only possible states are 0, 1, and 2. So notice this is P0, P1, P2. Sorry, it's as I'm writing, it's kind of fixing the way I write, so sometimes it's harder to read. So the probabilities are 16/37, 12/37, and 9/37. This part we've done a few different times, but any questions on the steps here? So from here, now we want to get all the different things. We want to find E of N, E of T, E of W, E of NQ. And so you have these here, and we're going to be using those in the next part. So if you haven't already, write down the 3 probabilities, because we're going to use them for the next part. So find all the little pieces. And they'll be added, there'll be an added in question, which we'll find out is not really something we want to do. So it should be that when I add it up, I get 1 is equal to 37 divided by 16 times P0. So, oh, did I write? It's supposed to be 37 over 16 in the previous page. So I had 1 plus 3/4 plus 9/16. So that should add up to 37 divided by 16. Sorry about that. I'll write it when I do the calculations here. I'll put it in. But yeah, it should be 37. As I said, as I'm writing, it's trying to smooth things out, and sometimes the smoothing is changing numbers and so on. So E of N is fairly straightforward, as it usually is, for the finite ones at least. So we're just going to do 0 times probability of 0 plus 1 times probability 1 plus 2 times probability 2. So 0 doesn't matter, of course. And so we're going to get, that's equal, 1 times the 12 over 37 and 2 times the 9 over 37. And that's 30 over 37. Oh, so N is the total number of people in the system. So people being served plus the people waiting in line. And let me write down while I'm at it. Next, we're going to get E of NQ, where NQ is the number of people just in line. If I go back to the last one, obviously if there's no one in this system altogether, there's no one in line. If there's one person in the system, that one person is being served by the one server, which means there's no one waiting in line. If there are 2 people in the system, one person is being served and one person then is waiting, so we get that. At this point, we know that E of N is equal to lambda E of T, but we remember from the last class or the class before that the lambda in that case is the average arrival rate. And if there are 2 people in the system, the arrival rate is 0. So we have to get the average arrival rate, lambda A. So if you look at the last graph, at 0, the arrival rate, the arrow going forward, so remember when we have the lambda is equal to 3, even though lambda is 3, that 3 people are arriving per minute, we only can move one at a time. And since we're MM1, 2, the most number of people that can be in the store is 2. So this part here, P2 is saying we have 2 people altogether. And since there's one server, one of those 2 people is being served, which means only one person is waiting in line. It's confusing, but remember that the graph I gave before doesn't include time. So the bigger the lambda is, the faster things move, and the bigger the mu is, the faster things move, but it doesn't change the different things. So if you go back to the last page, at 0, the arrow going out, the arrival rate is 3. So therefore, we do 3 times probability of 0. If I look at 1, again, out of the 1 state, the arrow going out is also 3. So the arrival rate at 1 is also 3. If you look at 2, you'll see that no one else can arrive. So therefore, the arrival rate at, if there are 2 people there, is 0. And I get 84 over 37. As always, you're checking my numbers here. And now we can use little sim, because now there's the average rate that we need. So E of t is equal to this 1 over average arrival rate times E of n. Make this 5 over 14. And I can use it also for W. The relationship still works, except now it's compared to E of n q. So W is, so let me remind you, T is the total time I'm in the system. W is just the time that I'm in line. So I get 3 over 28. And there's a second way of getting E of W, so you can double check yourself, which is we also know that the time we wait in line is equal to the total time we're in the system minus the time it takes to be served. The expected value for the time it takes to be served is strictly exponential, so it's always 1 over mu. And that will be true as we go forward, whether we have 1 server or 2 servers or however many servers we have. And since here mu is 4, I think it was. So E of W is equal to 1 divided by lambda A, E of NQ. And W is average time in line. So if I put this in, where I put in the mu is equal to 1/4, I should again get the 3 over 28. I'd have to double check. It could be I messed up the arithmetic. Average time, so that is, so you say average time in line is E of NQ divided by mu A. That should be a lambda A in this line. So this is 1 divided by lambda A, which is this number here. Okay. All right. So let me add in density function type thing, and then you'll see we don't really want to do it. But any other questions on this part before I move on? Okay. So let's again find the density function for t, the total time we're in the system. And let me remind you of the couple things. So these were our conditional density functions. You'll see that we don't really need to worry about these because I'm going to tell you it's not something we can easily use. But so this is what we have. And so again, we get this. But it'll become a little bit shorter because if I get there and there are two people there already, what's going to happen? Because we're doing MM1, 2. So it's going to basically, so that probability isn't going to be 0, but we can't enter. This part drops off because if I get there and there are two people already there, the store is full, I can't go in. That third term I don't need. And from before, we found the probability of 0 is 16 over 37. We know that for 0, it is mu e to the negative mu t. Mu is 4. So that's that first term. The probability of 1 is 12 over 37. And according to the formula up here, that's then going to be 4t times 4 e to the minus 4t. So I get that. And there's our density function. And it just doesn't simplify. So with the infinite one, when we had MM1, the infinite part actually made it easier. I can simplify this a little bit. By factoring out the 4 e to the negative 4t. But you can see it's still kind of a pain. And the reason it's kind of a pain is now if I want to use this, what type of integral will I have to do to get the antiderivative of this? And that would be integration by parts because I have t times the exponential. So it's not that difficult, but you have to do integration by parts. And if I did MM1, 3, there'd be a third term with a t squared term. and then I have to do integration by parts twice. MM1, 4, I have to do it 3 times, and so on. So in theory, we can do this, but in practice, it's not something we can easily put on a quiz or test. On the other hand, it is something I could put on a take-home quiz. So could come up in a take-home quiz. So MM1, the infinite case, is actually easier than MM1 finite in terms of a density function. Okay. So any questions on this? Okay. So what we now want to do, and obviously we're not complete it today, is we want to do similar things for MM2 and MM3 and so on and so on. So if there's more than one server. So today we'll see how far we get, but probably we'll just get to getting the, which I think we might have done already, getting the steady state probabilities. Might as well keep it simple. So let's start with one where it's just lambda is equal to 2 and mu is equal to 2. So lambda is fixed. Mu is, the first one is 2. But we did one of these. Do you remember what this becomes and why? So first, what does it become? What is that rate? So someone says 4. And remember, the idea is at this point right here, there's one person in the store, which means only one of the servers are working. This says that each server can serve 2 people per whatever the time is. So in the first one, only one is working, so they work at a rate of 2. If I have 2 people, they're both servers are working, and so now they can serve 4 people. On the other hand, once I get to 3, it doesn't change because there's still only 2 servers, and therefore they're still only working at the same time. The third person is just going to have to wait in line, and same on forever. And as with the last one, we can get the probabilities. So P1 is equal to, again, I can read off like this, is equal to 2 over 2, so 1 times P0. P1 is equal to 2 over 4, so 1/2. That's a P2. P1, so therefore 1/2 P0. So when I'm here, there's one person in the store. They're being helped by one server. Each server can deal with 2 people per, let's say, minute. So since there's only one server working, if there's one person in the store, that one person can serve 2 people per minute. If I'm here, where there are now 2 people in the store, they're both being helped by a server. Each server can serve 2 people per minute, which means the 2 of them together can serve 4 people per minute. And once we get to here, we now have 3 people, but we still only have 2 servers, so one of the 3 people in the store has to wait. And so again, we're having 2 servers working. Each of them can serve 2 people per minute, so for a sum of 4 people per minute. Is that okay? Okay. And we continue. You can see from now on, so here P3 is again from the graph 1/2 P2. which is 1/4 P0, and dot, dot, dot. I just keep multiplying by 1/2. And I have P0 plus P1 plus P2 plus P3 plus P4 plus dot, dot, dot. I can pull out P0. I get this pattern. Is this geometric? So is this a geometric series? The one series you're supposed to know. And the answer is no, because remember, geometric means I need to multiply it by the same thing to get from one term to the next. Let's go from the first term to the second term, I multiply by 1. Get from the second term to the third term, I multiply by 1/2. So the ratio is changed. On the other hand, it becomes geometric. Starting here, it is geometric, because to go from the second to the third term, I multiply by 1/2. I multiply by 1/2 again. I multiply by 1/2 again, and so on. And so for this part of it, everything except for the first term, I can use the geometric sum, which remember is a over 1 minus r, where a is the first term, which is this one. And the ratio is 1/2, so r is 1/2. Therefore, all but that first term add up to 2, which means that the sum of all the terms is 3. The 1 plus the 2 of this rest of them. So plugging in, P0 and P1 are both the same, both 1/3. P2 is the half of that, P3 is the half of that, and so on. And this will be typical of MM2 or 3 or 4, is they aren't quite geometric, but they eventually become geometric. In the handout, in the packet, I get a formula for it, but for me, I just remember it as geometric and do it like I did here. So we could try to make a formula in general for MMC, but I find it more trouble than it's worth. Okay. So any questions on this? Obviously, we have to do more of them, but any questions on this? Okay. So let me do the usual quick intro with the next one. Obviously, we're not going to have time to do it. Is once we get this, we want to get the same thing we did for MM1. We want to get E of N, E of NQ, E of T, E of W. And in theory, at least, the density function. So let's start it and see what happens. So this is E of N. In some ways, this is not the best first example to show that we're going to have a possible problem here. Because again, I ask, is it geometric? You remember from MM1 that no, it's not the geometric. It's going to be derivative of the geometric. But like the steady state probabilities, what's going to happen in general is it's not even quite going to be the derivative of a geometric, because there'll be possibly terms at the beginning that don't fit the pattern. And therefore, it'll end up being easier to actually get E of NQ first. because even Q starts when we start having the geometric pattern. And so what we'll get next class is, I won't make you actually do the calculation to find it. We'll just get a formula for E of NQ. In theory, you do it similar to how we got E of N for MM1, but this time I'll just give it to you. And then once we have E of NQ, we can easily get E of W. Once we have E of W, we can get E of T. Once we have E of T, we can get E of N. So in MM1, we start with E of N and work our way around. In MM2 or 3 or so on, we'll start with E of NQ and work our way around. So let me stop there. So there's a homework in the Q sections. Start working our way around. I'm kind of jumping a little bit around, and we'll jump around in a little bit. And as I said, I am roughly following the notes that are now on Blackboard. So you can look at that. You can also look forward and backwards because I'm not following it exactly. So if you want to get ahead and see what's going on and so on. And again, hopefully tomorrow, but probably Friday, I'll put up on Blackboard the first take-home quiz, which will be due Monday, March 30th. So as I was saying it, someone asked when it was due. So the first take-home quiz will be due Monday, March 30th. That might change depending on how many problems there are, but we'll figure it out. Also, as I said, and I'll send out an announcement, 1 of 3 days next week, we're just going to meet either in Blackboard or Zoom or somewhere else where we're just going to come together so you can talk to each other in working groups. So if I forget, you'll send me an email reminding me that we're going to do that one day next week. So that's it for today. I will stop the recording in a minute, but let me quickly ask if you have any questions. So if you don't have any questions, we're done, and I'll see you tomorrow. If you have any quick questions, stick around. Oh, so right, I knew I forgot one thing. Someone's trying to talk. I can't understand. Once I get out of this, the same place where you get the Collaborate Ultra, you can get the recordings. But because that's kind of a pain, I am also downloading it and putting it on my YouTube channel, which I should have put a link on under one of the announcements in before. So if you can't find that link, let me know. Oh, sorry. So E of NQ right now, we're not going to do. We're going to wait until tomorrow to get it, and I'm just going to give you a formula for it. Oh, so and then as I was saying that, so NQ is the number of people in line as opposed to N, which is the total number of people, which is the number of people in line plus the number of people that are being served. So go back to the previous example, you can see more exactly what it is. As I said, we'll get a formula for it here tomorrow. Anything else? Well, I'm going to stop the recording, but if you have questions, let me know.